Now we visit a very special equation under the category of differential equations, and that is called the Cauchy-Euler equation. The Euler's equation, Cauchy-Euler equation, they are one and the very same, and one has to look very carefully at the form. When we have taken differential equations of the second order linear, we have done constant coefficients. Earlier we have done constant coefficients in a separate lecture, but now we wish to point out that the form of the Cauchy-Euler equation is a naught into not d2y dx2 only, but there is an x squared term, a1 not only dy dx, but there is an x term, so x to the power of 1, here x to the power of 2 and d2y dx2, and a constant into y is equal to, on the right hand side we have a function of x. So this is called a non-homogeneous equation, because if we had fx is equal to 0, we would have called it a homogeneous equation. When the right hand side is a function of x, then it is called a non-homogeneous equation. Hence, the Cauchy-Euler equation is, first of all, second order first degree defined, but it is not with constant coefficients. The coefficients of d2y dx2 has x square, dy dx has x, and y has a coefficient of a2. This part is of course a constant, and a1, a0, a2, they are all constants. So we will see how to convert this by a very simple substitution into an equation which has which is of the form of a second order linear equation with constant coefficients. So that is the focus of the Cauchy-Euler process, to convert this kind of an equation into one that has constant coefficients tagged on to the derivatives of the different orders. Here we have of course a second order derivative as the highest. So we will rub out and see how this can be processed and converted to, again I repeat, a second order differential equation with constant coefficients. That is the focus of this method. I put it back once again because I wish to emphasize that if we divide the entire equation by a naught, then the first coefficient can be taken as 1. If a naught is not 0, then we still retain this flavor of a second order equation, and we can write it in a modified form, which I am going to do right now. X squared d2y dx2 plus e1 x dy dx plus a2 y is equal to some function of x. Now the substitution we are going to use is very simple. We have to observe here that the function that we are looking for as a solution is y as a function of x. So y is the dependent variable, x is the independent variable, and we are looking for a solution of y in terms of x. Now we use a very simple substitution. That means we would like to convert this equation into one that does not involve x, but into one that involves y again as the dependent variable, and x is asked to leave this place, and we invoke through the substitution another new variable which we call z. So, if we do that, let us see what happens. If we write x is equal to e to the power of z, then obviously z is log base ex. So, this is the substitution that will do the trick, will lead us to the desired goal, that means will lead us home. Now, with this substitution, we are going to evaluate x dy dx and x squared d2 by dx2 in terms of dy and dz. So, let us do that first. We rub out this part and let us see. No, this equation can remain on the board. First of all is the substitution says x is equal to e to the power of z. Now, dy dx is dy dz into dz dx. This is via the chain rule. Differentiate y with respect to x is y with respect to z and z with respect to x. That is nothing but dy dz, and as we said, z is log x, so dz dx is 1 by x. This immediately leads us to the fact that x times dy dx will be dy dz. So, here we have our first conclusion, x times dy dx is dy dz. So, this is one result which we can block. We see that this term x dy dx gets replaced by dy dz. We will take this a little up and differentiate it once again to see what is the value of x squared d2 by dx2. So, we rub out this part. We remember that x is equal to e to the power of z. So, we capture the substitution here, x is equal to e to the power of z. That's fine. And then write this a little on top so that we have space for differentiation. So, we just now got x dy dx is equal to dy dz. We differentiate both sides of this once again with respect to x, and then we write d dx of x dy dx is d dx of dy dz. In other words, if we do a differentiation of x dy dx by the product rule, we first get this implies x d2y dx2, x d2y dx2 plus dy dx into 1. This is the product rule applied to x dy dx. First function, differentiation of second. Second function, differentiation of first, which is 1. That is d dx of dy dx. That means we can write this as d dz of dy dz into dz dx. So, this we can write as d dz of dy dz into dz dx. So, this is very clear. In other words, if I just continue a little more, but this I will take to the top. Cauchy equation is modified, fine. We just need the substitution up there. So, taking this on top and noting that dz dx is 1 by x, we will write this as from here x d2y dx2 plus dy dx is equal to d2y dz2 into 1 by x. We now multiply by x. So this leads to the fact that x square d2y dx2 plus x dy dx is equal to d2y dz2. Now, we know that x dy dx is nothing but dy dz. So, for a while we just buy a little bit of space by rubbing out the equation. We carry on here. In fact, we can rub out this part as well. So, this implies that x square d2y dx2 is nothing but d2y dz2 minus dy dz. That's it. So we see that here we don't have any z or y multiplying the dy dz and d2y dz2. So we again bracket this particular fellow in a box. We're going to summarize. When we take an example, we will use these results, not derive them again and again. And I will quote the expression for x to the power of 3y dx3 without giving a proof, because it's one more differentiation of this, and the result I will just write down. Now, by one more differentiation of this particular result, one will get another similar looking expression, that is for the third order derivative. X cube d3y dx3 is d3y dz3 minus 3 d2y dz2 plus 2 dy dz. We are not doing the differentiation again, but interested people can try that and see that this indeed does work out. We are not likely to encounter more than third order differential equations, so most of them will be the second order type. So this result and the earlier result, that dy dz is x dy dx, is very important. So we will capture them before we write down some problem to see how the method works.